Okay, good afternoon, everybody. We've come to the last problem-solving session of the semester. So just so you know how the rest of the semester is going, there are no more lab classes. So if you're in one of the 232 sections, those are done. Although if you're in, if you have any late lab reports, you'll have until Thursday at 3:15 if you're in that section, or Monday at 9:45 if you're in the 100 section, to get those, to get any lab reports you may still have out in. Points will be deducted for lateness, but you still have the opportunity to get those in. Otherwise, we'll be going over problems now. Monday afternoon, we will review the last three chapters, and chapters 28 through 30, and then on Wednesday, next Wednesday, the 23rd, at this time, will be the exam. And I plan on grading the exams in the evening. So basically, as soon as I finish dinner next Wednesday, I'll get back to grading the exams. And the goal is to have the grades for the class done by the time I go to bed next Wednesday. So when we get to Christmas Eve, those will be taken care of, and you won't have to worry about looking for your grades past that point. So that everything should be done on the 23rd. So with that, let's go over the 6 problems that we have. So the first is a mutual inductance problem. So you're asked to determine the mutual inductance per unit length. So basically M divided by script L between two long solenoids, one inside the other, whose radii are R1 and R2. So R1 is the small radius, and R2 rather is the small radius. R1 is the big radius. And so, and whose turns per unit length are N1 and N2. And again, the check with mutual inductance is if you work both ways, do you get the same answer? So that brings us to number 8. An air-filled cylindrical conductor is 2,800 turns, and it is 2.5 centimeters in diameter and 21.7 centimeters long. So A, what is its inductance? And you've got enough information to figure that out. B, how many turns would you need to generate the same inductance if the core were filled with iron of magnetic permeability 1,200 times that of free space? So now you're using the value of L you had in part A. You're replacing mu naught with mu, which is 1,200 times mu naught, and then you're solving it for a new value of N. So how many turns would you need given an iron core to get the same inductance? For question 11, to demonstrate the large size of the Henry unit, a physics professor wants to wind an air-filled solenoid with self-inductance of 1.0 henries on the outside of a 12 centimeter diameter plastic hollow tube using copper wire with a 0.81 millimeter diameter. The solenoid is to be tightly wound with each turn touching its neighbor. The wire is a thin insulating layer on its surface, so the neighboring turns are not in electrical contact. So how long will the plastic tube need to be, and how many kilometers of copper wire will be required? What will be the resistance of the solenoid? So for the first question, the length of the plastic tube is going to equal N, the total number of turns, multiplied by the diameter of the wire. So make sure you differentiate between the diameter of the tube and the diameter of the wire. But if the turns are tightly packed, are tightly wound, then the length of the tube is going to be the total number of turns multiplied by the diameter of the wire, which is the width of each turn. And so you solve that equation for N, plug that into the inductance equation, and then solve that for script L, the length of the wire. And then how many kilometers of copper wire will be required? Well, that's N, which you can now solve for, multiplied by 2 pi times the radius of the tube. And so that gives the, uh, so that's the circumference of each loop in the coil, and you multiply that by the total number of loops of the coil. That'll tell you how much copper wire you'll need. And then you're asked, well, what is the resistance of the solenoid? So you'll need the resistivity of copper. So you'll need to go back to, I think it's chapter 26. No, 25 is the resistivity of copper. And then multiply that by the length and divide by the cross-sectional area. So that's the cross-sectional area of the wire. So you'll need the radius of the wire to solve part C. And so that's how you do number 11. It's a bit involved, but if you follow the steps, you should be able to go through it. The next problem is number 19. So for the toroid of figure 3026, and so that is on page 3026. That's at the top left of page 806. So you see a circular segment, and it has a thickness H. So determine the energy density in the magnetic field as a function of R. So, so you need the magnetic field of a toroid, and remember the energy density is B squared over 2 mu naught. So B is just the magnetic field of a toroid as a function of R, which is the distance from the point inside the toroid to the center of curvature. And so then you're going to integrate that over the total volume. So break the integration into 2 parts. So you have a circular cross section and then a height of H. So there's no height dependent term. So you can multiply multiply U, which you solve for in part A, by H. And then you're integrating over a circular cross section. So the differential element of a circle is R dr d theta. So you'll need to integrate over theta from 0 to 2 pi, and then integrate over R, not from 0 to R, but from R1 to R2. And so setting up the integral is the hard part. Doing the integral is actually easy. The last 2 problems are LR circuit problems. So we have how many time constants does it take for the potential difference across the resistor in an LR circuit to drop to 3% or 3.0% of its original value? So keep in mind, the potential difference across the resistor is equal, from Ohm's law, equal to the current times R. And here, in this circuit, if you look at page, let's get that up. So that's figure 30-7. That is on page 791. So basically, the current is built up to its maximum value, and then you flip the switch, so you're bypassing the power supply now. So the current is going to go down to 0. But remember, the inductor is going to oppose that change. So it's going to take a measurable amount of time for the current to go down to 0. So this is like a discharging capacitor. So the current is equal to the maximum current times e to the negative t over tau. And so you multiply both sides of the equation by R, and you have the voltage across the resistor is equal to the maximum voltage across the resistor times e to the negative t over tau. And then you can solve that for t as a number times tau. Then for problem 25, this is the last one. Determine the energy stored in the inductor as a function of time for the LR circuit of figure 30-6a. So here, the switch is connected so that the power supply is part of the circuit, and you're building up from 0 to a maximum current. And So you know the current is a function of time. We went over that in class. The energy stored in the inductor is equal to 1/2 Li squared. So you write that as a function of time. And then after how many time constants does the stored energy reach 99.9% of its maximum value? So you're going to figure out what the maximum energy is from part A. And then again, you're solving for t as a function of tau. Now, because there's a squared term in there, you have an extra step that you need to take into account. Okay, so any questions on the problems?
Happy snow day!
Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8 of you. So I will break you into 4 breakout rooms. Okay, so I will take care of problems 3 and 4. And so the rooms you have correspond to the problem you're doing. So I'll have 2 of you do problem 1, 2 of you do problem 2, 2 of you do problem 5, and 2 of you do problem 6, and then I'll do problems 3 and 4. So go ahead and get started on those, and then at 4:25, I'll come around and see how everybody's doing. Okay, so let's start with the first of our problems. And so this is the mutual inductance problem. So do I have a volunteer for this one?
Yeah, I'll give it a shot.
Okay.
So the mutual inductance would be equal to N1 times the flux of 2 that acts from 1 over I2.
Okay. All right.
So the flux is equal to B times A2, but B is equal to mu naught times N1 I1.
Okay.
So the flux in total would be equal to mu naught N1 I1 times A2.
It's N2 I2 because you want the flux due to the second coil that's acting on the first coil.
Right, okay.
So it looks something like this.
Right.
And
so the I's cancel.
Right.
And the A is equal to pi R2 squared. Right.
Right. And so the I's cancel, and what are you left with?
That's N1, N2, mu naught pi R2 squared.
Yes. So the flux per unit length. So capital N is the total number of turns. Small n is the turns per unit length. So you have the flux is equal to the total number of turns in the first coil multiplied by the magnetic flux that the second coil, due to the second coil that's through the first coil. So you need the magnetic field due to the second coil, which is mu naught times small n2 times I2. But then you're dividing that by I2. So the I2 terms cancel out. And you're multiplying that magnetic field by the area, which is pi R2 squared. And so, and then to go from the inductance, the mutual inductance to the mutual inductance per unit length, you're just dividing capital N1 by L, and that's small n1. And so you get the product of small n1 and small n2 times mu naught times pi r squared. And if you work the opposite direction, you would get the same results. So if you had n2 times phi12 over I1, you would wind up getting the same result because you're only interested in the portion of the magnetic flux caused by the first current that crosses through the second coil. So you'd still have the pi r squared term for the area. So any questions about this? Okay, so that's the first example. So now we're going to move on to the second example, which is the cylindrical inductor, or at least the simple one of the cylindrical inductor problems. Do I have a volunteer for that?
I can.
Okay.
Right, so you're just trying to find the inductance of the solenoid. The formula for that, I'll wait for you to.
Go ahead.
All right, the formula for that is L is equal to mu naught times the number of turns squared times the area over the length. Yeah,
Right.
you got it. So you input the values that are given by the question and you solve for inductance, which is 0.022 henries.
Yes.
Now you want to solve for the you want to solve for the amount of turns in the solenoid required to I forget what the number was. Hold on. 1200. Okay, yeah. So you're trying to find the number of turns required to change the inductance, or not the inductance, the
So to keep the inductance
the
the
permeability
same.
by 1200.
Yeah.
Right. So you're just solving for the number of turns. You use the exact same formula, but you multiply the permeability by 1200. You input the values, and the answer you get is 81 turns.
Right. So again, plugging the numbers in. So you're using this value of mu, and then this is the inductance in script L and R squared, or which are the same values that you used up here. And so you get 81 turns. So it took, let me get back to that problem. It took 2,800 turns without the iron to produce that inductance. But with the iron inside, it only takes 81 turns of wire to get the same inductance. So any questions on that particular problem? Okay, so now we're going to go on to the third problem. There are a couple of ways you can do this, but the basic gist is you're building a 1.0 Henry inductor. Given a 12 centimeter hollow tube, so the diameter of the tube is equal to 12 centimeters. The diameter of the wire is 0.81. And was that centi or milli? That was millimeters. All right, so this is what you're given. And you're asked to find first, how long is the tube? So you set up the equation for the inductance of a solenoid. So L is equal to mu naught. Well, we know what that is. N squared divided by the length of the tube multiplied by pi times the radius of the tube squared. Okay, so in order to go any further, we need to figure out the relationship between the length of the tube and the total number of turns. Now, the total, that relationship comes from this. So the length of the tube, you have one loop right after the other. So you're basically packing in those loops as tightly as possible. And so that the length of the tube is equal to n, the total number of turns, divided by the width of each turn, which is just the diameter of the wire. And you can then solve this for n. N is equal to is equal to the length of the tube divided by the diameter of the wire. And now we can write this equation so we only have one unknown. So that's mu naught. N squared is the length of the tube squared. So that's L tube squared divided by L tube. So you just have L tube in the numerator. And then the diameter of the wire squared in the denominator. And you're multiplying by pi times the radius of the tube squared. And so you want to solve this for the length of the tube. And so that's equal to the inductance that we desire, which is 1.0 henries, times the diameter of the wire squared. So you multiply both sides by that. I guess it really didn't need the parentheses. And then you're dividing by mu naught pi and the radius of the tube squared. So that's 1.0 henries. The diameter of the wire, that's 8.1 times 10 to the negative 4 meters. And you're squaring that. And then mu naught is what it always is, 4 pi times 10 to the negative 7 Tesla meter per ampere times pi. And then the radius of the tube is 6 centimeters, so 0.060 meters, and you're squaring that. And so you plug all those terms in, and you get 46 meters. Or no, excuse me. 46 meters. And so that's the length of the tube. So that's, that's pretty much the full length of the hallway in Smithtown Science, that 46 meters. So that's the length of the tube. So that answers the first part of the question. And then the second part, how many kilometers of copper wire will be needed? So the length of the wire is equal to N, the total number of turns, multiplied by the circumference of each turn, which is 2 times pi, or 2 pi times the radius of the tube. So N you can solve for here, from here, and since we have that information now, that gives 5.7 times 10 to the 4 and that's N. So basically you have to be prepared to wrap the wire around the tube 57,000 times if you actually want to do this. So then you plug those values in, and again, using the radius of the tube, which we know, and that value of N, we then plugged all those in, and we're asked for how many kilometers. It comes out to 2.1 times 10 to the 4 meters, or 21 kilometers of wire. And so you need to start with 21 kilometers of wire. So that's an awful lot of copper wire that you need to make this inductor work. And then you're asked for the total resistance of the wire. And so that's the resistivity of copper times the length of the wire, which we now know, divided by the cross-sectional area. So that's pi times, and this is the radius of the wire now, because you want the area of the wire. And so rho here is, going back a couple of chapters, that's 1.68 times 10 to the negative 8 ohm meters. And then that's 2.1 times 10 to the 4 meters in the numerator. And then pi times the radius of the wire. So that's 4.05 times 10 to the negative 4 meters and squared. So that's the radius of the wire in meters. And so what you get, I'll bring this up to the top because I have space for it. R is equal to 700 ohms to two significant figures, or 0.70 kilo ohms. So any questions on that? So again, the key is figuring out the relationship between the length of the tube and the total number of turns in the wire to figure out how those are related. And once you have that, everything else falls into place. And so again, the length of the tube is equal to the total number of turns of wire multiplied by the width of the wire, which is just its diameter. And then you can use that to solve for the length of the tube, and then how much copper wire you get from that is equal to n times the circumference of an individual loop, and then you just go from that. So any questions about this problem? Okay, so let's move on to the fourth problem, which is the calculus problem. I refer you to the diagram because I think it makes more sense to figure out what's going on if you look at the diagram. So the first thing you're asked is the energy density. And we know from class that's b squared over 2 mu naught. But the magnetic field inside the solenoid depends on r, which is the distance from a point inside the toroid to the center of curvature. And so B is mu naught n I over 2 pi r. And you're squaring all that divided by 2 mu naught. And so you have mu naught squared over mu naught. So that becomes mu naught n squared I squared. So here you get 4 pi squared, but you're dividing it by 2 again. So you have 8 pi squared. And you have r squared. So now you have your energy density as a function of r. So the energy density is not uniform inside the toroid, which means that if you want to calculate the total energy stored inside the toroid, you're going to need to integrate to get that answer. So for U, or for capital U, you're integrating, which is the total energy stored, it's equal to the energy density integrated over the whole volume. So we can write this as, and you look at the diagram, you have a circular cross section. So the radius is going from R1 to R2. So it's not going from 0. You're integrating from R1 to R2. So you have a circular cross section. So putting all these terms in. So mu naught n squared I squared over 8 pi r squared r squared. And most of this is going to eventually come out of the integral because it's constant. So you have the circular cross section. The differential element of an area of a circle is equal to r dr d theta. So if you were to integrate r dr d theta over a full circle, you would get pi r squared. You're integrating theta from 0 to 2 pi. You're integrating r from 0 to r. So that's r squared over 2. And so it's 2 pi times r squared over 2, which gives you pi r squared. So that's how you figure out the area of a circle. Here, we're not integrating over the full circle. We're just integrating from the inner radius r1 to the outer radius r2. And we have the additional term dh for the thickness of the rectangle, or for the height of the rectangle. So we'll bring the constant terms out. So that's mu naught n squared I squared over 8 pi squared. There's a square term here. So you're integrating dh from 0 to h, but there are no other height-dependent terms. You're integrating theta from 0 to 2 pi, but there are no other theta-dependent terms. And then you're integrating rdr over r squared from r1 to r2. And that simply becomes dr over r. So again, the trick to this problem is setting up the integral. Actually doing the integrals aren't that difficult. This integral is simply h. So you're basically multiplying by the thickness of the rectangle h. And you're also multiplying by 2 pi because you're integrating over the entire circle. And then this term, this integral, is just the natural log of r2 over r1. So you plug those in. And so you have mu naught n squared I squared. You have 2 pi divided by 8 pi squared. So that just leaves 4 pi in the denominator. The h you can leave up in the numerator. And then you're multiplying by the natural log of r2 over r1. So again, the key is setting up the integral. So you're integrating over a circular cross section, or over a segment of the circle, and that's going from r1 to r2, but it's over the entire circle. So you're integrating theta from 0 to 2 pi. And then you just have the height term for the thickness of the rectangle. And of those, the energy density only depends on r. It does not depend on theta, and it does not depend on h. So you do those integrals, that simply becomes h. The theta term simply becomes 2 pi. And then you're integrating dr over r. So you're left with this natural log term. So any questions about this? Okay, so that brings us to our 5th problem. Actually, I didn't want to close that off. That brings us to our 5th problem, which is the time constant for the current to go back down, as it's going back down to 0. How many time constants does it take to get to 3.0%? So do I have a volunteer for this? Well, okay. So for this, it's equivalent to a discharging capacitor. So you're starting at the maximum value. And you're exponentially decaying. So it goes down exponentially to 0. And like I said, it's the equivalent of a discharging capacitor. And you're asked for the voltages rather than the currents directly, but all you're doing is multiplying both sides by R. That I times R is your voltage as a function of time. Multiply, I max times R is your maximum voltage, which is what you had initially, times e to the negative t over tau. And then you just go through the steps to solve for t. The first thing you do is divide both sides by V max. And now you have V over V max is equal to e to the negative t over tau. You take the natural log of both sides. So you get the natural log of V over V max is equal to negative t over tau. And then solving for t is easy from here. So t is equal to negative tau multiplied by the log of v over v max. And so we're told we want to get to when it's 3.0% of its initial value. So that's, we want the natural log of 0.030. And so again, the natural log of a number between 0 and 1 is going to be negative. So the negatives will cancel out. And what you're left with is 3.5 times tau. So it takes 3.5 or 3.5 time constants to drop for the voltage across the resistor to drop down to 3.0% of its initial value. So any questions about this? Okay, so that brings us to the last problem, which is about the energy stored in the inductor. And so we want that equation as a function of time. And then we want the time it takes for the energy stored to get to 99.9%. Do I have a volunteer for this problem?
I can do it.
Okay.
So we started out by saying that I as a function, or the current as a function of time, is equal to V over R times 1 minus e to the negative t over tau.
Okay.
And where V is equal to V naught in this case.
Okay.
And then U equals 1/2 Li squared. So then we just plugged in I, the equation that we got for I, in the I squared. So it ended up as 1/2 L times V naught squared over R squared times 1 minus e to the negative t over tau. That whole thing squared.
Okay.
And that
So that's
was,
part A.
yeah. So then for part B, we said that 0.999 times LV naught squared over 2 R squared is equal to LV naught squared over 2 R squared times 1 minus e to the negative t over tau squared.
Okay.
And that whole thing reduces down to 0.999 equals 1 minus e to the negative t over tau squared.
Yes. 1 minus e to the negative t over tau squared. Okay.
So then if you take the square root of both sides and then subtract 1 and multiply by -1, you get 5 times 10 to the minus 4th is equal to e to the negative t over tau.
Okay, so is equal to 1 it's equal to 1 minus the square root of, and what did you say that was?
That was 5 times 10 to the minus 4th, or 5.00 times 10 to the minus 4.
Okay. All right, that sounds about right.
And
Okay.
then I did ln on both sides and got negative t over tau is equal to negative 7.6, and then you get t equals 7.6 tau.
Right. And so that's negative 7.60, and so t is equal to 7.60 tau. So yes, so t is equal to 7.60 tau. So it takes 7.60 time constants for the inductor to get 99.9% of its maximum energy. Okay, so any questions about this example? So any questions about any of the examples we covered today? Okay, so we're basically done. Like I said, there's not going to be anything, there's not going to be any lab tomorrow or Monday morning. So we will meet again Monday afternoon, and we will review for, chapters 28 through 30 for the exam, which will be on Wednesday. So otherwise, have a good weekend. enjoy the snow. Don't go out driving tonight, but and hopefully you won't have too much shoveling to do in the morning. But make the most of the weather, and I will see everybody on Monday.